Now this is a short video that covers air resistance and drag in projectiles. Now there's not really many calculations that go along with this one, however in an exam it will most likely be a short answer question where you have to explain the theory behind resistance and how it affects a projectile. So air resistance affects a projectile in all dimensions, so that's the x and y, which affect both the time of flight and the range. Air resistance acts in the opposite direction to motion. So motion, as outlined on this slide, is given by the blue vector, with the direct opposite in green being the air resistance. This is the equation for air resistance, which you don't need to know. However, you can see the terms that are involved in it. The terms include air density, or the density of the fluid that the projectile was moving. So it can also be applied to water, for example. The area of the object, so that's the surface area of the object. With the bigger the object, the greater the air resistance, as it is proportional to the force. And then CD is just a drag coefficient, which relates to the smoothness of the object. But you can see here the key term, velocity. Now, it's velocity squared, which is proportional to force. So a slight increase in velocity will increase the force a lot more. So velocity is the most important factor in air resistance. Now, as mentioned earlier, the air resistance acts in the opposite direction to the direction of motion. So in this case, it would be air resistance is a green vector, and you can see that a green vector. You can see that this green vector would have components both in the horizontal and vertical directions, and it can be broken down as such. So typically we look at projectiles in the absence of air resistance. However, if we do take it into account, so if we look solely in the y direction or the vertical direction, the velocity when launched from the ground will be reduced due to the air resistance. Now this obviously has an effect on the time, as the velocity will be at a lower value. So the time taken will be reduced and the maximum height will be reduced. Now it's interesting to know that when the object is on its way down, the air resistance is still there affecting it, and the time for it to reach the Earth from its peak is actually increased as compared to when there is no air resistance. When compared to a scenario with no air resistance, the maximum time to come back to Earth will be decreased due to the object having a lower maximum height. Now when we focus on the projectile in the horizontal direction, when subjected to air resistance, the overall range will be decreased. The overall range is decreased because of the effect of air resistance in the horizontal direction and the reduced time of flight. So combining all this information, the projectile will actually fall more steeply than it rose, which means it is no longer a symmetrical parabolic shape. So what I've done is actually flipped over to the textbook, and this is the diagram that I'd like you to have a look at. So the black line represents the theoretical parabolic path with no air resistance. Now, due to air resistance, a lower maximum height and a lower range results in this shape. And you can see in the black line, it is symmetrical about the center here. However, the blue line, it falls more steeply than it rose due to the air resistance. With the formula that we saw before of air resistance, we didn't use the mass of an object in calculating the force. Now, the mass does not affect the amount of air resistance, but it does affect the degree to which the projectile is affected by the air resistance. So for example, if you're throwing a ping pong ball compared to a baseball, the degree to which the projectile is affected changes. And this means a light projectile will be affected greater than a heavy projectile.